Yes. So I'll click on OK. So your material has been saved. This will be in the small screen itself. Sorry for that. Okay. So so now material has been given. For that material I need to create a section for that. So what section is that? It is homogeneous solid section. It is homogeneous, and I'll give this as a plate. Okay, name as a plate. So give continue. Your section will take material as steel. Again we have an option here, plane stress strain. These plane stress strain are for your planar problems. Okay, this is a solid problem, so you don't require it. So I will just ignore that. I will not click on that. It is material steel and solid. So steel, in the sense you will be having in an assembly, you will be having n number of components and n number of materials. So you will be getting an option which material for you require for your particular section. Okay, so for the plate section I am taking solid homogeneous and the steel as a material. Now this section has been created, that need to be assigned to your material. Click on to assign section, select to the geometry, and it will create its own set. Set means for that particular results it will give. So I'll take that set as plate. You can create a plate as a name of that set. So now okay, so click on done. The plate will be a section which I have created previously, and type is solid homogeneous and material will be steel. Click on OK. As you can see that your material has been assigned. The color is changed of your geometry. Okay. Next, once this whole thing is done, that is material, you can view how many materials are here, the list. If you want to go edit, any edition of your material is required. Okay. Then any assignment has been done wrong or not, you can cross check them. Again, the assigning of your sections is done correctly or not. Okay, so you can check that. So once this is done, moving to the assembly. Assembly, you create an instance in the sense your coordinate system will be to the origin. From there your calculations will be done. So I will create an instance of the part. Okay, and here this instance will be dependent or independent of that particular assembly. In the sense, this particular part of your assembly is independent of mesh what you generate automatically, or it is dependent. So you can take, if dependent, you need to, when you do a meshing, you need to change for module for that particular model. Okay, or if you take independent, your assembly will take defaultly as an whatever the size you are giving. Okay, so I'll take dependent so that I can show you. So you can see your coordinate system as at the center where you have started. Okay, you can move this also by giving a translate instance. Your coordinate system also can be moved wherever you require. Okay, so that is what. Next, moving further is a step. In this step, so first thing is create step. Step in the sense start step. Whatever your problem starts, your Abaqus only read from star step itself. If your star step is not given, it will not read at all. Okay, so for that star step is very important. So star step, in the sense step, what is your solving or your name of your solution? So I will take it as a modal analysis. Modal analysis. So initial step will be there already, which will be required, and now you can see that various different type of solving options are there. Direct, cyclic, dynamic, implicit, explicit, temperature displacement, geostatic, heat transfer, mass distribution, diffusion, soil, general static, static risk, viscous. They are different type of solving methodologies or different physical problems, what we call typically. So R is doing a modal analysis. For that, linear pretribution. Linear pretribution in the sense it will solve by taking a linear values. So there is buckling, frequency, static linear distribution, static state dynamic, as well as substructure generation. So we require only the frequencies in the sense we want to check the modal analysis or the frequency of our body. So I'll click on to frequency and give continue. Now you can see here there are different methods to solve the same modal analysis. That is, 3 methods are there. Eigensolver with 3 methods. One is your Lancruz method. What you have solved your equations in M1, M2, M3. Your Lancruz method of reducing the points or iterations, what you call Lancruz iterations, you have done in your M3, right? So same methodology of your iteration methods it will solve. And the other is subspace and AMS. So typically only 2 we will be using, that is subspace or Lancruz. Lancruz is used as a best method anywhere to get a natural frequency or eigenvalue, what we call natural frequency or eigenvalues, that is a lambda value. Okay, so Lancruz, I have used as a Lancruz here. And the next is number of eigenvalue requested. You require all the range of your frequencies, means you have n number of frequency mode shapes. It will give all, but it takes longer time. So typically what is like, we have mainly we look into 8 to 9 mode shapes only. That is, first 6 mode shapes are the critical mode shapes, what we say, or the critical frequencies. In general practice, the first 6 modes are the critical frequencies, which will be very what we call very dangerous, or it will get resonance to the vibrating or anything. So these are the critical natural frequencies or the critical eigenvalues. For that we always take a range. You can take any numbers like 50, 30, 100. How many values you require, how many frequencies you require, you can give. For all, it will give all. So value, I am giving only 8. 8 means I will be getting 8 mode shapes or 8 natural frequencies. And the second is frequency shift. If you want to certain range, start with 100 frequency or 200 frequency. If you give that, it will start. And the minimum cycle time and the maximum cycle time you can provide for other thing. For modal analysis, it is fine for default. So don't change anything here. Use Lancruz and use your number, any number for 10. Okay, and block size, direct and value. If your block size, in the sense in the frequency band, how much block size you require for each frequency change. So what we'll do, we take as a default as a practice. Okay. Now there is one more as option as other, is like matrix storage. How your matrix should be solved, default, unsymmetric, symmetric, right? For certain problems we use solver default, and certain problems we use symmetric. We don't use unsymmetric only for few cases, extreme cases of a temperature based. For that we use unsymmetric. Okay, normalization vector, displacement or mass, how you require, it will take. So I require a displacement, I'll consider that. Okay, now your step has been created, that is star step, that is a frequency, star frequency has been taken. Next, going back, interaction, we don't have any interaction because we don't have any other components, only one component is there. There is no contacts need to be built. You can see that constraints need to be built or rigid elements need to be built to connect anything. So we don't require here any contacts kind of things. Yes. So moving further, load. Now for modal analysis, we don't require, or to calculate a natural frequency, we don't require external load, because it's a virtue of a body For initial excitement, it will be oscillating for number of times. So we don't require load. Only we required is a boundary condition. So what is that boundary condition? How it is arrested, how it is attached, or how it is behaving for particular load, or particularly it be natural behavior. So for here, if I give this without load, this becomes a free modal analysis. That means to check whether the assembly is done correctly or not. Only to check we do a free. For that we don't require any load or boundary condition. So I'll do that, and then we'll go for fixed analysis. So here no change, no load, no boundary. So next is your mesh. So how do we do it? We seed it. Seed in the sense split the entire section into number of points. So click on that. Now we can see that dependent part instance cannot be edited or assigned mesh attributes, because I have taken there to create an instance as a dependent. So what I'll do, I'll change here assembly is there, I'll change that to part 1, and then click on to the seeding. So seeding, it is giving 1.2 as a default element size. So what I'll do, I'll take as 1, so that I'll get more finer mesh. Okay, other things you keep as a default one. So you apply here, you can see the points here, simple points. That means your end has been discretized, or it has been splitted up of that particular size. Each will be having 1 or less than 1. So average will be the 1 size. So clicking on that. Next is your mesh part. Prior to that, I want to check mesh control. If I want any few, like what type of element I want tet elements, or I want hexa predominant, or hexa with penta mixed. So I'll do with tet, and then I'll delete and I'll show you. Okay, so click here and then click on to the mesh part. So OK to mesh the part, click on S. You can see that your tet elements has been generated. Okay, again you can check which type of elements has been assigned here. So shape matrix, size matrix, and analysis check. If these colors in the mesh has been generated, that means those mesh are failed. So again, now our element size and mesh quality is important. So what is this mesh quality or element quality, what we generally talk about? So element quality is nothing but generally whatever we do a mesh, it should be having, if I consider a hexa mesh, it should have perfectly, all sides should be have 90 degrees, right? All the angles should have 90 degrees. But as a simple geometry, it will be having. For the more complex geometry, your angles will be distorted or changed in certain angles. So that how much limit it can be changed, or why we are restricting to certain angle to be changed? Because the result of your FE or the output what we get depends on your mesh elements or mesh quality. Why? Because certain elements which are extended, if I take this as a distorted or tet elements, certain angle for the maximum or minimum angle, it will not, the mesh point will not take the load itself. It will just pass the load. It will not deform. So that it will not be accounted to the entire calculation or your entire simulation or summation results. So that will be ignored. This element will be ignored. For that itself, that if that is ignored, your results will vary. So if your result vary, that will be having a long gap. Yes. So for that itself, the element qualities are also important. Again, I will give a list of element qualities what are need to be checked. Okay. So as of now, you just consider this element qualities should be taken. So what are the element qualities? I will give a checklist of that. So what are those individual qualities and everything? I will explain them. Okay. So as of now, we are taking the same and what type of material has been assigned associated with that. So where do I show? No, 1 second. Okay, this is here. What type of element we are using? Typically, it is standard, explicit, two types. Explicit in the sense, for explicit problems, we use explicit elements. It's nothing but it will be having certain secondary orders or the element deletion or certain things which only accounts for the transfer of loads. But standard in the sense, we have all the standard formulations. So again here there are different type of elements required for different solving. So for structure type we use 3D stress itself. For acoustic problems, that is CFD problem, cohesive or adhesive problems, there are different type of elements required to get the different outputs. Okay, for us it is standard 3D. Okay, you can see this numbering C3D10. That means it has three noded element with D in 10. That is 10 node or 10 nodes has been present in this particular each element. That type of quadratic tetrahedral element is this, or tet element it is. Okay, that is a second order. Typically tet 10 noded is second order, tet 4 noded is a first order. Okay, so this is one. And next, if I take different like hexa mesh, it will give C3D20R, that is reduced integration. These are the element types what we call typically. They are all come under again 1D, 2D, 3D. For Abaqus they have different naming, reduced integrated or integrated. You can see if I use R, reduced integration, like integration points what we call, as you studied in your FEM, like how you calculate your displacements and other things from integration between the two. It will do an interpolation for two nodes and you calculated the displacement. Okay, so for that reduced integrations, so that those kind of things. I have done it with tet elements. Now I want to change it. How do I do? Click on the seeding. If it is okay, click on that, change the type. So for that, go to assign type, go here, change this tet to hexa. Click on OK, delete mesh. It will ask whether need to delete the previous mesh or not. So click on it, your mesh has been deleted and the mesh control has been assigned. Now click on to the mesh, your mesh has been generated. Okay, so but your mesh is not much looky, what we call typically the straight, following a straight line or a finer mesh. It should look neat. For that again you can add a mesh control here. So hexa predominant, refine the sweep mesh. Okay, so click on that, delete mesh again, click on this, you'll get a part as meshed little bit finer with the penta elements. Okay, initially it was only like hexa, now it is hexa dominated. You have penta and hexa both, or you can even use hexa penta both with little finer. So I'll use here 0.5. Apply, the seeding has been done. Now click on the part. So now you can see your fine mesh. So that means your number of points of solving has been increased. So again, it comes into how do you decide your element size? People might ask, or it is a general practice why we use particular size, why, how to use that particular element size. I can use 1, I can use 2 here also. So how do you decide your element size? It is by practice or by conversion study. There are 2 type of conversion study. One is P type and one is N type. P type is changing the type of element. N type is changing the order of elements. First order, second order, those kinds. So again, it is by practice or by conversions and or by previously done the same machine. Here it is very simple. We don't require much of thinking. You can use any, and based on your configuration of your system also. Like you have high-end machine, you can use finer mesh to get more accurate result. Okay, if you don't have, because the solver time also is very important. If takes a small problem takes 2 hours, there is no use of doing it when finer mesh, because results are approximate itself. So you can use based on the your configuration of your system also. So now mesh is done. Optimization is not required here. Now as job, click on job, create a job. Now you can give your free analysis. So what I have done, I have given a free name of that job. So continue. Now here, as you give everything, it is in queue. If you have number of solving, so one another you are giving, you can give a queue or a background run and full analysis or restart. Restart in the sense, certain times what happens, we have the huge model, like for complete automobile, your car model is there. So it cannot be run one or 2 days. It takes around 15 to 20 days to run, or 4 to 5 days with the high-end machines. For that what happens, sometimes something happens, your run might stop, your power starts, something had happened, hardware has issue. Whatever the time has been used to solve that should not be wasted, right? So for that a restart option is there. So wherever it is stopped, when you give again a run, it will start from there itself. Okay, so that is the option of restart. A full analysis, because it is simple, I am doing it. Okay, give OK. Your job has been generated here. Now prior to submit, what I will do, your software takes a default location of solving. Okay, like set working directory. Okay, so it takes default at wherever your software has been installed, that is C drive as a temp file, but I don't want, I require my file separately. So what I'll do, I'll go to here, I'll take this value, I'll change that. So your files, whatever you run, give a save, it will be saved on that particular folder. Okay, so click OK here. Now go back to prior to run, give a save. So you can save as a Modal CAE. Okay, so Modal 1. So I have clicked here and click on to the job manager. Here there are options. Write input in the sense your deck, whatever have you created, like star step elements types, which load, what is the boundary condition and where to end, that will be written. Data check is your check need to be done, whatever you have applied is being correct or not, and submit to give a run. And monitor, to monitor how your problem has been solving with a step wise, where your step has been solving or what is an error or warnings it is giving. So you can check that and the result to visualize. Okay, so already I have created a job. If you want to edit it, go back, any change, memory, anything, you can change the memories, everything. Here it is very simple, so I will keep all the as a default only. Okay, now I will give submit. Now you can see the monitor. Here you can see the step, what step it is solving, increments, attempt to increment that. Okay, server, which server it is connected, everything. These are related to time step, time, everything. Okay, you can see any error it will display here, any warning it will display here. Output, how many number of frames. Okay, so data file, your results in your DAT format, that is your ASCII format. You can see that your mass, effective mass, everything has been calculating. And message file, any errors or anything you need to check here. Status file is your run has been completed or not. It is giving the run is successful. Now the run is done. You can see the status, it is completed. So results, click on results, it will automatically go to your visualization. So here again you have n number of options here. You want a deformed, anything changes, or you want to check the deformations or the results, view the results. So you want to change the size, go to viewport, view annotate. Here whatever the display you have, so that can be changed on this format. So legend, in the sense we call this as a legendary. So your display, how you require, whether you require a scientific way or a fixed way or an engineering way. So I'll take fixed way, so that precise will I take 4, so that after decimal point how much you get, and set a font, it is very less, so I'll increase that to 14. Now you can see it is fixed. Engineering, you can also take that. It will change after decimals what you require. Now you can see your displacement magnitude. Now the question is, so you are saying displacement, but we are doing a modal analysis. So where do a modal analysis comes with a displacement? We are calculating a natural frequency for result 10. I have requested 10 natural frequencies. As you can see, 10 modes are there. Yes, all the 10. This is a first mode. How it behaves, what is the frequency? As I have said, we have done a free analysis. The first 6 modes will have 0, equal to 0, because this is a free analysis to check whether the assembly is being done correctly or not. What if the 7th also, or 7th to 12 also are 0? If in an assembly there are 2, like your water bottle and a cap, if this assembly is made not done correctly, cap and this, so this body has 6 rigid modes, this body has 6 rigid modes, that is degrees of freedom, this body has 6 degrees of freedom. So this will move in 6 degrees without deformation, this will be moving with 6 degrees. So there you will be getting all the values. 12 degrees of freedom as 0. There will be no 7th frequency will be having a positive value. Okay, so then you can say that if 7th value has a positive, your assembly is being done correctly. First 6 are equal to 0 or near to 0, that means your assembly is done correctly. If 2 bodies or 3 bodies are free, each body will have 6 degrees of freedom, so 6 rigid modes. So 3 body or 2 body are free, that means it gives a 12 rigid modes. That means all the